In this video, we're going to practice calculating some probabilities with a contingency table or a two-way table sometimes called, and particularly focus on those or probabilities, or sometimes they're called a union of events. So in this example, we have 1,137 American adults were surveyed and asked whether or not airports should use full-body X-ray machines to screen passengers at security checkpoints. Below is the summary of responses based on party affiliation. So we have the party affiliation of the person that they asked, whether they were a Republican, a Democrat, or an independent, and then either they said should use, we should not use them, or perhaps they didn't know. We've also got the totals for both the rows and the columns, which will make a lot of these probabilities much, much easier. So let's start with part A here. Part A says, what is the probability that a person in this survey was an independent or answered should use? Now, that word or is going to be the thing that we want to look out for and the thing that we're going to practice in this video. When we're talking about or probabilities, the formula for an or probability, probability of A or B, is equal to the probability of A plus probability of B minus the probability of A and B. So in this problem, we're going to say, let's call event A independent, so probability that they were independent or said that they should use it is equal to the probability that we select an independent plus the probability that they said we should use it. Oops, let me clean that up. Minus the probability that they were an independent and said we should use it. If we can find these three things, then we just have a little bit of addition and subtraction to do, and we'll have our answer. So we're going to start with the probability that we select an independent. So in this case, here's my independent row. This is really nice because they've given us the total. So if I want to talk about the total number of independents, well, I've got 450 of those individuals, 450 independents out of a total of 1,137 people in my survey. I'm looking at this number right here. So we looked at the total number of independents. You could also, if you really wanted to, take 351 plus 77 plus 22, but they gave us the total there anyway. So there is the probability that I select an independent. Next, I'm going to talk about the probability that the person said that we should use these scanners. So I'm going to look at this and I'm going to say, okay, well, the should use, that is this row right here. So in that row, I have a total of 914 individuals saying that we should use these scanners out of a total of, again, 1,137 total people in my survey. So I'm adding these two, and I think intuitively that makes sense. Yeah, if I'm looking for this or that, I should add them together. The thing that we often forget when we're calculating or probabilities is this minus probability of A and B. And that's because we've counted this number twice. We've counted the 351 individuals with both the independent group and the should use group. So for that last part, if I say probability that they are both independent and should use, I'm going to highlight that, probability that they are independent and should use, I'm going to say, okay, well, what's the overlap between those two? How many people are both independent and said we should use them? Well, there's 351 of those individuals divided by 1,137. So at this point, I've got everything I need. I can just go ahead and add and subtract my numerators. I already have a common denominator. It's 1,137 for each one. So that part doesn't really matter. We can just go ahead and add the numerators. 450 plus 914 minus 351. So I ended up with 1,013 divided by 1,137. Or if I wanted to give that as a decimal, that would be 0.8909. So there is my solution. So it's that and probability that we want to remember to subtract every time because it is going to pop up relatively frequently. Not always, but most of the time. Let's look at another example. So if I look at part B, working with that same data set, what is the probability that the person in the survey was a Democrat or answered don't know? So using my formula again, you don't necessarily have to write this formula out every time, but I do think it's helpful the first few times. I want to talk about the probability that the person was a Democrat or said don't know. We'll say just don't. How about that? I want to make sure that I'm consistent. We'll say don't know. We'll just write it out. Don't know. Okay. All right, so I want the probability that the person selected is a Democrat plus the probability that they said don't know minus the probability that they were a Democrat and said they don't know. All right, so starting with the probability that they were a Democrat, looking at this case first. So for my Democrats, I have 369 of those individuals. So I have 369 of those individuals divided by, again, I'm selecting from my total group, and if I go back and look up at my total group, that was the 1,137 of those individuals. So I have 369 divided by 1,137 plus the probability that they said they don't know. So again, I'm going to scroll back up and I'm going to say how many individuals said that they don't know. Well, I'm looking at this row right here. There were a total of 53 individuals that said that they don't know. So 53 out of a total of 1,137 minus the probability that they said they were a Democrat and they don't know. So how many Democrats said that they didn't know? Well, there are 15 of those. I'm looking at that overlapping region between the two, the intersection sometimes it's called, between those two variables. So 15 out of 1,137. Out of 1,137. And what's nice is, again, because we have the common denominator of 1,137 for each of these, you could just take 369 plus 53 minus 15 over 1,137. That would work as well. But I'm just going to go ahead and add my numerator here, 369 plus 53 minus 15, and I ended up with 407 out of 1,137, or if I wanted to give a decimal, that would give me 0.3579 rounds to 80. So we would say 3580. So these are my answers for part B. All right, let's take a look at our final part of this example. Let me just make sure I've got enough room. Last question says, what is the probability that the person in the survey was a Democrat or an independent? Now, it turns out this question is going to be a little bit different. It's still an or probability, so we're still using that same probability of A or B. So I want to know the probability that the person was a Democrat or an independent. So, okay, if I use my my or probability formula, we said, okay, let's take the probability that they were a Democrat plus the probability that they were an independent minus the probability that they were a Democrat or independent. So, okay, let's go ahead and look at these. Let's start with the probability that we select a Democrat. So I need to go back and look at my survey. So let's erase, so we're starting with a clean slate. So the Democrats, we said 369 of those individuals, so 369 Democrats out of a total of 1,137. So 369 out of 1,137, plus the probability that I select an independent. So I'm going to scroll back up and I'm going to say, well, how many independents did I have? So here's my independents column, and I had 450 of those individuals, so 450 out of 1,137. So let's see, we said 450 independents out of 1,137 minus the probability that they were a Democrat or independent. So I'm going to scroll back up and I'm going to ask myself how many individuals were both Democrats and independents. And if I look at this, there were none. There is no overlapping region between my Democrat column and my independent column. So this is an example where we have two mutually exclusive events. You cannot be, at least from the results of this survey, you cannot be both a Democrat and an independent. So what that means for me is that the probability of being a Democrat and an independent, if they can't happen at the same time, is simply just 0. I don't care about that part. I can just focus on the 369 plus 450. So 369 plus 450, it gives me 819. So 819 divided by 1,137, which gives me 0.7203 if I wanted to round to 4 decimal places. So there is my probability. And so this is the last thing I kind of wanted to end this video with, is if we have two mutually exclusive events, if A and B are mutually exclusive, meaning they cannot happen at the same time, then, well, we know just probability of A or B in general is just probability of A plus probability of B minus probability of A or B. Excuse me, probability of A and B. A and B. But if they're mutually exclusive, then this probability has to be 0. So we don't actually care about this part. So that means if A and B are mutually exclusive, I can just take probability of A plus probability of B, because there is no probability